things from one season to the next. That's the origin of measurement. We begin to learn about time and distance, and slowly we map out the world around us, the things that we become familiar with, using this idea of measurement, of comparing things. And that's exactly what has happened. And over the years, the centuries of our civilization that we have managed to keep going, we've reached out into the vast. You can see the clouds that Ian was talking about in the last talk, and into the imperceptible. We've discovered microbes and bugs and atoms, and we've reached out here. And the thing that has enabled us to do that is measurement. It's measuring things and then seeing what happens. It's enabled us to have ideas about them, but it's measurement that's at the heart of it. And that's why the key thing I want to communicate to you, that science is not about maths. So the way science is taught, it always seems to be embroiled with mathematics and complication that just puts people off, frankly. Maths is about a very specific way of working out logical consequences, a way of thinking, but science is about measurement. Okay, that's the first thing. The second thing is to tell you what measurement is. You can never make perfect copies. And so if you want to make a measurement in one time and place and connect it with a measurement made in another time and place, you have to have this traceability back to these standards. And each time you do that, there's an extra little bit of measurement uncertainty. And whatever you do, you can never make a measurement that's got a lower uncertainty. the International System of Units, and I normally have a rule for talks, which is one talk, one thing. Just talk about the thing that you're going to talk about. It's quite a simple rule, but I'm going to break it. Today I'm going to talk about two things. I want to talk to you about the International System of Units, but first I'd like to tell you about my system of units. So it's a system of measuring that I've invented. It goes like this. It's got a standard length. That's called a Michael. Standard Michael for two things. This is a big problem in measurement, is that this is so it's really, really precious, and I'd like to put it in a safe and leave it alone. But I can't, because it defines the system. I've got to keep taking it out when I want to make fresh copies. So it's both defining what we mean by them, and it's the seed for the dissemination, the realization, as it's called. So let's see how we make some submultiples of a Michael, and then we'll see how to make a measurement. Here's a Michael. Now we want to make halves and quarters. So we create a Mitch, two Mitches, and we check that the ends match up so that they're equal in length. And then we put the Mitches end to end and see that they may add up to one Michael. And then we can be sure that they're a half a Mitch each, a half Michael each. So now we can make measurements in the world. So here's an unknown length, and you can see that it's one Michael, put two Michaels together, and then three Michaels. Okay, let's get rid of that one, and we have a half. You see, we've made a measurement. Now, the SI actually uses this kind of thing. That's 2.875 Michaels. We've gone from this standard thing by doing quantitative comparison. We've made measurements out of them. And that is how measurements actually, even in the SI, that's how they work. So we can do time as well. So we can just count maximums, throw a ball up in the air, count the number of pendulum oscillations, and it took 5 maximums. Let's just do that again. Then go up in the air, 5 maximums. Now you might be thinking, that's not very measure more complicated things out in the world. So, for example, here's speed. So that ball is going to shoot across the screen, and it's going to shoot across the screen here, and when it goes past the first line, the clock will start. When it goes past the second line, the clock will stop. So here it goes. So, whoa, fantastic. 1.1 Maxwells it took, and that's 2.875 divided by 1.1 Michaels per Maxwell. Now, my system of units is very, very thorough. I've put a lot of effort into this. And so we've got abbreviations for these units, and that's called the Micromax. In the SI, they've got the rules for, and did you remember Ian said 10 to the power 14 and 10 to the minus 1. When you divide by a unit, you put minus at it. So for meters per second, they say meters second minus 1. I think it's really rather recommended. In my system, we just put Micromax. I think it rolls off the tongue. I'm going to recommend it. And you can measure accelerations. So there you get speeds from each little clock, stopping and starting. So we get a table of speeds, and we can work out accelerations. That's 0.413 Micromax and max. And you can work out forces. You can stretch this thing a very long way. And that is my system of units. And I want to recommend it to you. There's the Sharmila, that's the unit of force. The Andrew, that's the unit of torque. And if you have met Andrew, will know exactly why that's the right name for the unit. And the Inshuk, which is the unit of pressure, the force. That's the number of Sharmilas per square mile. My system of units, I hope you noticed that the names are gender balanced, and they're also ethnically diverse. But perhaps well, there's something wrong with my system of units. Can anyone think of anything wrong with my system of units? Oh, damn, you got it first time. Only I know it. That's right, no one else uses it. And you might think, well, that's very nice. But the point about systems of units is their specialized language for communication. In the same way that philosophically you can't have a private language, it's nonsensical. In the same way you can't have a private system of units. And when we use units, they're not for our convenience or for my aggrandizement. They're actually to communicate with other people. And so it needs to be a shared system to work. Now there are a couple of other weaknesses also shared with many other unit systems. The first one is that thing I put. Change its length or weight, and this has happened to every unit system that has been created. At some point over a few hundred years, the fundamental standard objects that have been created have been damaged, often destroyed. In the UK, the standard pounds and yards were destroyed in a House of Commons fire. So this is a real risk. The second thing is we're trying to use the units for two different things. If you've got a standard unit, like I said, you want to keep it perfect and put it in a safe, don't touch it. But on the other hand, that stops you making copies of it. And then you think, well, you'd have a secondary standard, but then that's not the standard. It's a secondary copy. So you've got to make up your mind. There's this conflict there. And the last thing is the standard values are just completely arbitrary. Now the reason that I have wasted 10 minutes of my precious time here to talk about my system of units is I want to communicate to you that all system of units, just like my system of units, are made up. We just make them up. We invent all those words that you're familiar with, the meter, the kilogram, the Kelvin, all these things. People have invented them for particular reasons, particular conveniences. They have a history, but they're invented by people. And that's why I use this ridiculous example. Okay. So let's get on to the International System of Units. Now, these are the base units of the International System. There are 7 of them, and we sit them round a table like this to try and show that they're somehow of the same status. They're like the United Nations. There are some that are bigger and more powerful than others. So they differ dramatically in the concepts they use for realizing the units, but there they are. And there are lots of things right with this. So the thing that's most right is that everybody uses this system of units. It is humanity's universal system of measurement. And it's in the name. The clue is in the name. It's the International System of Units. It's not called MKS, it's not called the Imperial System, the British System. It's the International System. And this international agreement is at the heart of how it works. Some of you might be thinking, wait a minute, don't Americans still use pounds or something like that? And you know what, since the 1960s, well, they still do use pounds, but since the 1960s there have been no standard pounds. A pound is just a fixed fraction of a kilogram. Doesn't exist separately from the degree Celsius. So everyone uses the SI, but now the standard meter has been replaced by an idea, which I'll talk about, but the kilogram could still be damaged. It's still exactly like the standard Michael here. It's an artifact that could be damaged. And it could be just damaged, or more precisely, it could be corroding or changing in some way. Now, units such as the kilogram and the Kelvin still mix up this idea about being the seed of disseminating the unit and being the definition of what we mean by it. And the standard values are arbitrary, not natural. And for some of these reasons, we're going to change the definitions of 4 of the SI units. It's going to happen in May 2019, and it's coming to you. Now, let me try and explain why. So the definition of the second affects the definition of the meter, the candela, and the ampere. The definition of the meter affects the candela and the ampere, and the definition of the kilogram affects the mole and the ampere. So the kilogram here is at the heart of why we want to change the definitions of the system of units, because the kilogram is changing its mass. So the kilogram spends all its life in a safe. It's a very, very dull life. It was created at the same time as a large number of prototypes. The UK has a copy number 18 of the kilogram. That lives at MPL. And every 40 or 50 years, the kilograms from around the world assembled for a family reunion in Paris. And they're all compared to the... do you remember when you put your children up against a thing with the wall and you... How big? Oh, you've grown so big. They do that thing with the kilograms. They compare them. And they should all be exactly the same, but they're not. They're changing against the kilogram. Now, the kilogram, the international prototype of the kilogram, defines what humanity means by a kilogram. So it always weighs a kilogram. It doesn't matter how much weight it puts on. It still weighs a kilogram. If only that were true for me. And so what we see is all the masses of the kilograms in the world have all changed against the prototype, the international prototype. So what we have to guess is that the international prototype itself is also changing, but we have no way, even in principle, of detecting by how much. But if you guess roughly, you'd say it's changing by 1 part in 10 billion per year. So that's about 1/10 of a microgram per year. Don't panic. It's going to be okay. But from a meteorological point of view, it's completely unsatisfactory. But if you change the definition of the kilogram, you're going to affect the definition of the mole. That's the amount of substance, how many atoms there are in things. And if you change the definition of the kilogram, you're going to change the definition of the ampere. change wait a minute, there's the Kelvin there, it's just sitting there by itself. Maybe you don't have to do anything about the Kelvin. Maybe it's fine. You know, you just change yourself, I'm fine. But the Kelvin has its own problems, and so we're going to go to work on the Kelvin as well. So let me tell you about the new international to do. Why are we trying? I mean, did you have a problem with the old international system of units, sir? I don't think so. It's not what people knock on my door and ask. So here's measurement. It's quantitative comparison with a standard. And the question is, these standard quantities, could we define them a bit better? With the hindsight we have now of the 20th century of fantastic science, could we choose our units more wisely? So one of the things we measure with our unit systems is we measure things we think are fundamental constants of the universe. So we take kilograms, amperes, and kelvins, and we measure things like the Planck constant, the elementary charge, and the Boltzmann constant. This is a bit funny because the units are our human scale standard objects. But those things on the other side, the Planck constant, we think that's a truly constant thing. As far as we can tell, it's a real constant. And as our measurements improve, our estimate of the Planck constant just keeps moving around a bit. But that's wrong. It's the Planck constant that's constant. It's our measurements that are the changing. So what we want to do is to swap those things round. So the natural constants of the universe that we see are the basis of the system of measurement. And then we have unit definitions in terms of them, and then we use them to make the system that we use to measure. It's a changing concept of what a measurement unit is. Now, some of you might think, well, how do we know the constants are constant? Good question. And it turns out you can make a very good guess. You can look at the light from distant stars, and the light has come out of atoms in distant stars a long, long time ago. But you can see that the frequencies are very similar to light that comes out of the same atoms on Earth right now. And amazingly, you can do an experiment even in the lab right now that can detect very sensitively any change in the constants. This combination of constants here, called alpha, which has got the E squared over hc, that's the charge on the electron squared divided by the Planck constant divided by the speed of light. That combination of constants affects the frequencies with which atoms jiggle. If you hit an atom, it jiggles. So let me hit one there. That's an atom wobbling. And some of these wobbles depend on alpha, and some depend on alpha squared. So let's, yeah, you see that's wobbling much faster. So these are like atomic clocks where you set atoms wobbling and count the ticks. And you can set two atoms wobbling and see whether their relative frequencies changes over a year. And that's been done at NPL and at the German lab PTB, and the answer is the fundamental constants appear to be at least 1 million times more stable than the kilogram. That's astonishing. So if we were going to change the system of units to something that was 10 times better than the kilogram, that would be a useful change. The kilograms lasted 100 years. Decent bet for our civilization, according to the last speaker, is 1,000 years. 10 times should do us nicely. These constants are 1 million times more constant, more stable than the kilogram. So that's the thing that motivates us. Now, what we want to do is now to separate the definition of a unit from its realization. So we want to move these things apart. So the definition is what we mean, our idea of what we mean by a unit, and the realization is how we go about making it out in the real world. Now, the way we realize a unit changes over time. Think back 100 years to what a laboratory would look like. Clue, just look around you right now. technology in the next 100